Okay, you can see that we're back here at a Desmos webpage. It's a special one where someone has written a bunch of stuff that we see over on the left that'll help us to calculate areas of rectangles related to the area we want. Now, the first thing is you can see that the graph we want is y equals x squared. It looks something like this. So I'm just going to go up here and change this. This isn't something you have to worry about for a while. We are going to be using this a lot in chapter 5. So it'll be a while before we actually do anything like this. I only want to go as far left as 0, so I'm going to turn the left endpoint to 0. I only want to go as far right as 1, so I'm going to turn the right endpoint to 1. I'm going to zoom in a little bit. I'm hoping I can zoom in again. Let's just see. Yes, we can just barely fit it in, but I'm going to zoom out just once to see why. Now, I see what looks like a very jaggedy thing. I want to explain what's going to go on. I'm going to change this so it's drawing the rectangle slightly different, and I want to show you what happens when I just pick one rectangle. All right, now you can see this rectangle is a lot bigger than the region we actually want. It's very easy to see by the way the area of this rectangle is 1, since it goes one sideways and one up, but that's way too big. So the procedure that's going to be going on, and actually started with Archimedes a long time ago, is we start drawing several rectangles. This actually has a short rectangle and a bigger rectangle, and what we want to do is find the area of each and add them. And the web page actually does that for us. We can see that the area of those two rectangles together is 0.625. That's still way too big. You can see that it's way too big. So let's actually make this into 20 rectangles. You can see that the extra is getting smaller and smaller, and you can see that the calculated area is about 0.35875. I don't know that it'll actually let me go to 200. Let's just try that and see what happens. I can no longer even see the rectangles. Hold on a second. If I go to 50, I can see the tops of the rectangles, but they're starting to look more and more like the graph. If I turn that into 100, you can still see the little jaggedy things, and you can see that the area is getting close to 0.33 something. Now that's just an estimate, and the beauty of calculus is at some point we're going to have to stop doing estimates and find a real answer. Now if I try 1,000 rectangles, will it actually let me do this? It will. I can no longer actually see the different rectangles, but I can see the calculated area is now 0.3338335. Will it let me do 10,000 rectangles? It will. Now it's 0.33338335. You can see this is getting very close to a third. Now the beauty of calculus is the idea is what we really want to define the area is as what the estimates are getting close to, the more rectangles we actually use. If I use 100,000 rectangles, you can see this is getting very close to a third. That's no proof. We're going to have to use some algebra and the last great tool of calculus that we haven't talked about yet to actually come up with the correct conclusion that the area is a third.